All right, I am in my alternate location again because I got my oscilloscope, wave generators, and it's a beautiful day out, so the windows are open. There's a guy over there fixing his deck, so if there's like hammer noises, I apologize for that. I don't know what's going on. So I'm just going to jump right in and get to it here. We started with sound. I showed you some things about the vocal cords and how sound is produced. We got into a little bit about all kinds of information related to the speed of sound and how sound travels. And you had that document that you filled out, 26.1. Once we did that, we talked a little bit more about sound and how the speed of sound is going to change when you go to different environments because sound travels differently through different materials and sound travels differently through different temperatures. Most recently, we discussed the property of sound of frequency. And frequency is related to pitch. A high note is a high frequency, which has a very short wavelength. A low pitch is a low note, a low frequency with a very long wavelength. And we talked about frequency a little bit. We played the xylophone. We talked about what animals could hear. The Doppler effect, and why not do a little review of the Doppler effect right here. So we got a little Big Bang Theory going on, and here you go.
So what time does the costume parade start?
The parade?
Yeah, so the judges can give out the prizes for best costume. You know, most frightening, most authentic, most accurate visualization of a scientific principle.
Oh, Sheldon, I'm sorry, but there aren't going to be any parades or judges or prizes.
This party is just going to suck.
Oh, come on, it's going to be fun, and you all look great. I mean, look at you, Thor, and oh, Peter Pan, that's so cute.
Actually, Penny, he's wrong.
I'm Peter Pan!
And I got a handful of pixie dust with your name on it.
No, you don't. Hey, what's Sheldon supposed to be?
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it now, the Doppler effect. All right, I got a shower. You guys, make yourselves comfortable.
Okay.
See? People get it.
Great review of the Doppler effect right there. And so we call the bow wave as an example of when the source that's moving travels faster than the wave. And if the source is moving faster than the wave and the wave is a two-dimensional wave, that's what a bow wave is. And we also defined what a shock wave was, or cone wave. A shock wave is when the wave is three-dimensional. And it's still, the source of the wave has to be moving faster than the wave. And we watched some jet planes going through the sound barrier when we did that. So today, the whole goal of today is to get a little bit into what loudness is, or the intensity of sound. If I go back to that 26.1 document and just kind of scroll down a little bit, because really this is a great example of all of the notes for this particular unit, and we did it all in one day. As always, you could always pause the video, take down any other notes that you would feel like you needed to write down. But we're talking about intensity, pitch, and tone. Last class we talked about pitch, so today I'm talking to you about intensity. And intensity is the amplitude. Amplitude is a word that we had before. It refers to the strength of the wave, or how far the wave is moved away from the normal line. And that is loudness. That is intensity. That is amplitude. If you're talking about sound, a device that makes a sound wave louder is called an amplifier because it's affecting the amplitude. I'm going to show you how a sound can be affected by an amplifier, or basically what amplitude is. So we're kind of going back to the last unit when we defined some of those basic terms like wavelength, amplitude, frequency. I got to move my camera, so hold on just one moment. There we go. All right, I got my oscilloscope, which is showing us the wave over here. And I have my wave generator, which is setting a wave out of 392 hertz. 392 hertz means 392 waves per second. You can see those waves on the screen here. We can't see 392 because the time frame here is very, very, very short. This looks like it's like 3 waves or something. So there are 392 waves per second reaching your ears right now. The amplitude is the distance measured from the normal line. So in sound, amplitude refers to the volume. If I change this, which is the output level, I don't know if you can read those words, but if I turn the output so the output increases, obviously the loudness, it's louder now, and you can see the amplitude change on the screen. If I turn the amplitude back down, you can see the amplitude changing on the screen. Notice the frequency is staying the same. So therefore the wavelength is staying the same. The only thing I'm changing here is the amplitude. So when we measure loudness, when we measure that amplitude, it's actually measured in a unit called decibels. You may have heard of those before, especially if you're a music fan, because they often rate music concerts in terms of how loud it was or how many decibels, or car stereos or headphones. But a decibel is named after Alexander Graham Bell, the inventor of the telephone. So with our ears are really super sensitive to sounds, and I already talked about how we can differentiate between a lot of different pitches for sounds, a lot of different frequencies, but we're also really in tune to intensity. Different frequencies can sound more or less intense to us. Our ears are actually designed to pick up intensity sounds between the frequencies of around 2,000 to 5,000 hertz. And because that's what our ears are really designed to hear, those ranges sound more intense to us. The scale that we use, since it's measured in decibels, is called the decibel scale. And the decibel scale is a logarithmic scale. It's an exponential scale. That's basically what it means to be a log, is that it's exponential. Don't know why that page was taking so long, so I'm going to let it load, but that's what a log is. A log is an exponential scale. So for example, we do that to kind of compress the scale to make it a little bit easier to read, but sometimes that makes it harder for people to understand. On a regular scale without a log, if you wanted to go from 0 to 100, you'd need 100 lines. And if you take the same information and put it on a logarithmic scale, you only have to go from 0 to 2. And sometimes that concept's hard for people to understand. But what we're talking about is it's an exponential scale. So every time you move to a new box, that new box has a new value. So on the log scale, y is 2 equal to 100? Because that's 10 squared. The 2 represents the exponent. So this is a base 10 logarithmic scale. A 1 would be 10, and the next one would be 100, and the next box would be 1,000, and so on and so forth. So just a little bit more information about that logarithmic scale and how it works. I just made this slide to try to explain it a little bit better than what I just did. If you're going from 0 to 10 on a logarithmic scale, that's going to be 10 times louder. I mean, 0 means you can't hear it all, and 10 is 10 times louder than 0. So if you go from 10 to 20 on a logarithmic scale, that's going to be 10 times louder. But here's the catch, here's the key. What does this sound if you go from 0 to 20? Well, if 0 to 10 is 10 times louder, and 10 to 20 is 10 times louder, 20 is 100 times louder than 0. 10 times 10 is 100. So it's every time you go one box higher on the scale, you're doing a multiple of 10. So 0 to 30 would be 1,000 times louder. So let's look at that scale and just kind of get a feel for it. This page wasn't loading because my internet wasn't connected for some reason. So if you go from 0 to 10, that's a pin dropping. And 0 is hearing nothing. So a pin dropping is a very, very, very soft sound. So if you go from 10 to 20, leaves rustling in the wind, that's 100 times louder than nothing. And if you go from rustling leaves to a babbling brook, that's a decibel rating of 40. That's going to be 10,000 times louder than a pin dropping. Well, 1,000 times louder than a pin dropping. 10,000 times louder than hearing nothing. So every time you go up, it's getting not just a little bit louder, but significantly louder. So when you're at like a sporting event or a concert, I remember back a few years ago, not recently, but many years ago, the Bucks were in the playoffs, and my wife and I went to a playoff game, and I actually took a decibel meter with me to the game. It was recording 110 decibels regularly in the event, like consistently. So these are just some examples of things, that would have different ratings for decibels. A motorcycle, right around 100 decibels. Sporting event, 105. A rock concert, 110. Once you get up into this area, where you're getting into these darker reds, this is when you can start damaging your ears. So if you're damaging your ears, that means that eardrum, the membrane, and the bones and the fluid inside the ear, you can actually stretch out the membrane. and it's not going to be as elastic as what it once was. And if you do that, your ears are not going to be able to hear as high of frequencies as what you used to. That's what most people do to their hearing. They listen to music too loud, and that eardrum gets stretched out, and then they can't hear the fine high notes that they used to once be able to hear. Another thing that can happen if you listen or you were involved in really intense sounds for a long period of time is the little hairs that are in the fluid can start to vibrate just randomly, and that's called a ringing in ear. If you've ever been to a concert, a loud concert, and you have that ringing in your ear the next day, those are the little hairs still. It's almost like another auditory illusion where they think they're hearing something, but they're not. It can be really troublesome to have that when you get older. A lot of older people just constantly complain of this ringing in their ears, and that's a sign of hearing damage. It's a sign of hearing loss when that happens. So if you ever have that ringing in your ears, the best thing you can do is, not expose yourself to loud noises for a few days and to put yourself in a little bit quieter environment. So part of your homework tonight is going to be interpreting this graph. Okay, and this graph almost has like 3 different levels to it. You have frequencies across the bottom. We can hear from 20 to 20,000 hertz. That was covered in the last lesson. Today we're talking about sound level, or the intensity of the sound, or the loudness of the sound. And what you have here is this big solid black line. And the big solid black line, anything inside of this circle, that's what we can hear. So if you notice, most music is played between 50 and, maybe around 15,000 hertz or so. So this is, and because this is what's comfortable for us to listen to. And notice all of the music falls within the area that we can listen to. It wouldn't make sense to make notes up here because we can't hear that. And it wouldn't make sense to have the sound so low that you can't hear it. Likewise, I did tell you that on that last page where anything up over like 120, 125 decibels, these are the things that hurt us. Like you can physically feel pain in your ear if you listen to sounds that loud. But even so, a little bit under that line, you can still do damage to your hearing. Anything where you have a long exposure to loud sounds for periods of time can damage your hearing. So anything above this line is physical pain. So if you're listening to a frequency of 100 hertz at 140 decibels, that would be painful for you. It would hurt. Likewise, if you had 20 decibels at 100 hertz, we couldn't hear that because this line right here, this line represents, this is where we can hear. Anything below the line, we can't hear it. I can't hear 50 hertz at 40 decibels. I can't hear 100 hertz at 40 decibels. But I can hear 200 hertz at 40 decibels. So the same loudness, and I can hear it. And that's what I was talking about. Our ears are kind of designed to work in a really specific range. We're really good in the range of like 1,000 to 5,000. This is our speaking voice levels for most people. So you have some questions to answer, and it's going to be interpreting this graph. It's going to be like, can you hear it? Can you not hear it? Would this be painful? Would it not be painful? So one more time, anything inside the circle, you can hear. Anything above this line is painful, and anything below this line, you cannot hear.